This is team number 5. My name is Hugh and my teammate is NG Hong. We present our project MV2SIL, Reverse Engineering of 3D Extrusion Cylinders from Multiview Images. First, our motivation. CAD modeling is an integral part of computer graphics and has numerous applications such as architecture, art, and manufacturing. Motivated by versatility, we are particularly interested in reverse CAD problem, where a CAD representation is reconstructed from multiview images. Since CAD model can be tedious and require a certain level of expertise in 3D modeling, such methods would prove extremely useful in cases where manufacturers want to recover lost model from only images, or when sculptors and engineers want to fabricate model based on CAD but can't model CAD. And to our knowledge, this work is the first to tackle such a problem. Prior research in CAD recovery has been focused on reconstructing CAD from point cloud, which might require an expensive LiDAR system to capture. On the other hand, our method tried to directly predict geometry from given multiview images. The main idea is that while we could naively extract point cloud from NeRF-based volume reconstruction methods and plug them into aforementioned work, we obtain point cloud. The obtained point cloud is only an unreliable proxy which might add additional noise to the model. On the other hand, our method tried to directly learn edge geometry, which is a much stronger prior for reconstruction. So in our methods, we will first extract the edge using neural edge field approach, and this edge can then be classified using a volumetric semantic classifier. These label edges can then be directly used to reconstruct extrusion parameters that we are originally interested in. So as an overview, we are interested in extract a set of extrusion cylinder from a set of multiview images. These multiview images are obtained from rendering of Fusion 360 and ABC dataset. These synthetic multiview renders can be used as supervision signals to help the model learn to extract edges and classify them. More specifically, for each shapes of the dataset, we extract 50 multiview images uniformly sampled around the object. Then for each view, we extract visible edge information as input to the model. To evaluate our model, we have 3 metrics: exclusion axis error, exclusion center error, and per cylinder fitting loss. Based on these methods, our success condition would be to outperform naive point cloud-based reconstruction. Finally, as a future plan, we will first obtain the baseline comparison metric within this month, and within November we aim to complete our implementation, evaluation, as well as ablation study. Afterward, we aim to refine and finalize our projects. Thanks for listening.
Hello, I'm Prin from Team 6, and our group will be enhancing 3D Gaussian splatting via augmentation, regularization, and reflective rendering. A major question in rendering is, if we are given several views of a scene, how can we render other unseen views? Well, one way is neural rendering. These methods are popular because they achieve high render quality, but on the downside they do take very long to train and are also very slow at rendering. Some recent neural rendering approaches were able to achieve high quality renders as well as fast training, but they still could not achieve real-time renders. However, there is a new approach called 3D Gaussian splatting that is the first to achieve high quality real-time rendering. Here's how it works. Given a set of unlabeled images along with camera orientation and a point cloud generated using SFM, we want to render images from arbitrary views. First, replace each point in the point cloud with a 3D Gaussian. Adaptive density control is also implemented by splitting and cloning the Gaussians, and each of the Gaussian contains learnable parameters used for rendering. Importantly, a tile-based rasterizer is used for rendering. By using 3D Gaussians and a rasterizer instead of neural nets and ray tracing, this method is able to achieve real-time rendering. However, there are still some issues when rendering 2 specific kinds of views. First, views that are rarely seen during training end up looking distorted, and second, reflections end up appearing foggy. To handle the rarely seen views, we propose using self-augmentation to increase the views seen during training. We will periodically collect self-generated images while the model is still being trained. These will also include unseen views. We split training into 3 phases. First, a regular learning phase trained using ground truth images. Second, a novel review phase trained using the generated images that also includes the unseen views. But since these images are not perfect, we train using a lower learning rate to prevent the error from accumulating. This phase can also be thought of as regularization and a way for the model to review what it's already learned, hence the name. Finally, we have a contrast phase where we treat ground truth images as positives and generated images as negatives, then use a contrastive loss to steer the model away from inaccurate generated images and toward the accurate ground truth. But unlike the review phase, we don't use unseen views here. For reflective rendering, we propose adapting Kopnes et al.'s method of neural point catacoustics. In short, we'll use an additional 3D Gaussian to separately render the reflections. Finally, we experiment with other optimizers such as SAM. For our experiments, we use the MIP360, neural catacoustics, and synthetic blender datasets. Quantitatively, we aim to achieve better PSNR, SSIM, and LPIPS. We also want to achieve a rendering speed of at least 15 FPS. Qualitatively, we want to reduce artifacts in rarely seen views and achieve sharper rendered reflections. We plan to spend 2 weeks each on the data augmentation and reflective rendering approaches, 1 week for optimizer testing, and 1 week for evaluation and report writing. These are our references, and thank you for listening.
Hi, we are Dongwon, Jaehyung, and Junhyuk. We are going to introduce EPE, Equivariant Partial Point Cloud Post-Estimation. We are Team 7 and in the Noble Problem-Solving track. Our motivation is that it is hard to figure out the current object pose during the real-world experiment. It is because there should be an occlusion from the human, robot, and environment. The existing works are hard to use because they always assume the full point cloud. So this is our problem. There are 2 given point clouds. First one is the reference point cloud, which means there is only occlusion in the bottom side, and the point cloud is gathered from multiple camera viewpoints. The target partial point cloud is also gathered from multiple viewpoints, but there can be a lot of occlusions. So our goal is to estimate the relative transform between these 2 point clouds. And this is the previous work called equivariant registration. It decodes the correspondence-free equivariant features from given 2 point clouds and find the relative orientation between features. But it cannot handle partial point cloud inputs. To test this, we used 2 differently sampled partial point clouds, which is different from the original paper. And it shows poor performance on estimating orientation, as you can see in this qualitative result.
Let me introduce our main idea. We first encode observed partial point cloud from one viewpoint into local shape embedding. These embeddings can be trained with the local occupancy query rather than query points from entire shape. Then we introduce a specific merging operation in embedding space to merge the embeddings from multiple viewpoints into the one for full shape. Finally, we can calculate relative orientation by solving nonlinear optimization problem in embedding space. We already have our correspondence between 2 embeddings. We can easily solve this problem.
We decide to generate our dataset using ShapeNet. I'll briefly describe how we are going to generate the dataset. First, we sample object from the ShapeNet. Then we are going to sample to random associated rotation and apply the sample rotation to the object. Finally, we are going to sample a partial point cloud by merging a point cloud generated from multiple viewpoints. We assume that all camera parameters are known. During the point cloud sampling process, we are going to randomize the camera post and the number of camera in order to make the model robust on the viewpoint change and occlusion when our model is used in the real world. The distance between the partial point cloud and the full point cloud to correspond to the reference point cloud as loss function. In detail, our model predicts the pose of the object. We then measure the chamfer distance between the ground truth point cloud and the rotated point cloud based on the model prediction. We decide to use this metric rather than just geodesic distance to avoid ambiguity arising from the symmetric object. This is the plan for our remaining semester. Thank you for listening.
Hello, this is Team 8, Hae-Chang Kim, Haewon Lee, and Han Bi-jung. Let me introduce our project Multi-Dreamer. Recently, many models have emerged that can synthesize consistent multi-view images using just one single-view image, as demonstrated in the example here. However, these models do not always produce plausible results. We have observed significant distortion when objects with misaligned center points are combined. So in contrast to the baseline, we are planning to effectively handle a single view images of adjoining 2 objects as input. And we developed Multi-Dreamer based on this question How might we generate 3D meshes per object and then combine them into a single scene? Our project utilized the Model Sync Dreamer, which is a novel diffusion model that creates consistent multi-view images from a single view.
Now on, I'm going to introduce ROCA, which is novel end-to-end approach that retrieves and aligns 3D CAD models from a shape database. Core of this approach is differentiable alignment optimization based on dense 2D, 3D object correspondency and pro-cross alignment. This is the architecture of our model, which consists of three main parts. First, we leverage a 2D backbone to estimate both 2D object recognition and dense depth by using Mascar CNN and Resonate 50 FPN. In the second step, we utilize Edge Connect to fill incomplete parts of the 2D imaging. Then we can reconstruct 3D shapes of each object using Sync Dreamer. In the final step, we estimate 9-dimensional fill alignment of each 3D shape to the imaging, involving their translation, scale, and rotation. We first aggregate its corresponding features referred to as shapecode. By using it, we directly regress the scale and initial translation of 3D shape. At the core of alignment prediction, we use a differentiable weighted pro-cross optimizer that estimates rotation and refined translation.
To explain the inpainting part more detail, we'll utilize the inpainting model Edge Connect to recover the overlap region after the segmentation. The right images shows our toy experiment. After masking out the cat from the sofa, we could obtain only the inpainted sofa image. Here are the technical novelty and contributions. We propose an image 3D shape alignment module to consider the 9 DOF of objects to arrange them and utilize an inpainting model to recover overlap region. So we introduce a novel end-to-end pipeline for generating multi-view images from multi-object single-view images. We will construct dataset for combined objects from GSO dataset by ourselves, and our quantitative and qualitative evaluation plan is like this. And this is our timeline. Thank you for listening.
Hello, we are Team 9. We are in Novel Problem Solving track, and our project title is UFO Recon, Generalizable Sparse View Surface Reconstruction from Unfavorable Data Pairs. Similar to NeRF, we represent the 3D space with two fields, radiance field and signed distance field. For SDF-based volumetric rendering, we utilized NUS. Our task focuses on the generalizable surface reconstruction, which can handle general scenes. Also, the network should generate robust surfaces using only 2 or 3 images, which is often referred to as sparse view reconstruction. However, there is a very critical assumption which is called best view pair assumption. We found out that the previous works always assume the best pairs during both training and testing phases. However, in practice, we cannot guarantee the availability of the best view pair. It's more likely to have images from arbitrary viewpoints, making it more practical in real-world scenarios. The best pair is determined with view selection scores, which measures how informative each view is. The left figure shows the level of usefulness can be different from camera's transformations. Considering the real-world testing scenarios, we introduced the concept of unfavorable pair using lower selection score pairs or arbitrary pairs. We propose a novel task called reconstruction from unfavorable pair. We experimentally found that our baseline method outputs the generated solutions for unfavorable pairs. This is our experiment setup. The input is unfavorable sparse view images and the output is reconstructed surface. We use DTU dataset for all experiments. To evaluate the performance, we employ the chamfer distance. We expect that our method will be quantitatively better than the baseline and have qualitatively reasonable and smooth surfaces. To effectively address unfavorable pairs, we explicitly leverage feature similarity within the 2D domain to provide a robust geometric prior. In the left figure, if we project the blue point into 2 different views, their similarity in feature space will be high. Otherwise, they have low similarity. To sum up, the similarity score works like volume density. Moreover, if we consider occluded or unobservable regions, they are usually projected to different colors. To alleviate the multi-view inconsistency, we utilize perceptual loss, which exploits prior knowledge from ImageNet pre-trained models. However, naively utilizing perceptual loss would lead to over-smooth surface. Hence, we introduce a loss function called match-aware perceptual loss, derived from the similarity map. This loss function is basically a weighted sum of perceptual loss and MSE loss. Our objective is to construct a weight map to balance the losses effectively. This is our ongoing plans. We will implement match-aware perceptual loss and finalize our report and code base. Thank you for listening.
Hello everyone, this is Team 10. Our course project is NeRF-based trajectory optimization for quadrupedal robot. NeRF is trained directly on dense photographic images. They represent the geometry as a continuous density field, so they make it easy to use gradient-based optimizer. This is baseline work called NeRF navigation. This framework can make collision-free trajectories for quadrilateral drones using density from NeRF. They approximate the robot body using a bounding box. We can assume the probability of terminating a right leg from NeRF is a strong proxy of the collision probability. Then the trajectory optimizer makes set of waypoints that minimize multi-objective cost, including collision penalty. To produce optimal trajectory in online manner, we need an estimation of robot's current state. There are two loss components for state estimation. The first one is photometric loss between camera image and NeRF rendering, and second one is process loss from Bayesian inference. However, this optimization process cannot be easily applied to quadrupedal robots. Unlike drone which has single rigid body dynamics, quadrupedal robot has articulated dynamics with high joint dimensionality. This makes the dynamics model formulation challenging, and it requires additional sensors, terrain information, and gate phase data for state estimation. We tackle these issues by leveraging a deep learning-based estimator model. The estimator network takes the history of raw state, joint state, and controller actions as input values. Then they will jointly optimize the current estimation of robot state with photometric loss and ground truth. This allows us to reduce inference time and obtain accurate estimation without the need for complex dynamic equation. The entire process of our project is conducted within the Rysim framework. With an Unreal-based visualizer, it enables us to acquire image data required for NeRF training within Rysim. Additionally, we can construct PyTorch-based online learning code using Rysim Torch. The image in right side is our project environment in Rysim. We anticipate the primary improvement to be in the state estimation performance. We will use state estimation error as performance metric. Moreover, by comparing the success rate of entire scenario, we aim to demonstrate that improving state estimation can be beneficial for the overall online process. This is a table about our subtask and timeline. Thank you for your attention.
Hi, we're Team 11, Shoulders Up Giants. I'm Chorang Kim and this is Jino Park. Both of our baseline method, there is no global consistency. In each viewpoint, which is a unit iteration, information is not shared. This is our problem definition. Our model gets mesh and text as input, then generate texture image in UVMap format. Detailed idea will be introduced later. This is the first baseline method, texture. This model uses modified diffusion model to generate texture image on each iteration. Diffusion model receives depth map, previously rendered image, text, and trimap. Trimap is generated in each iteration, which contains three types of region in rendered image: generate, refine, keep. Text-to-text model use similar iteration, but they choose optimized 20 viewpoints in 36. And they suggest quantitative comparison method with FID, KID score. Our success criteria is based on this.
We consider two methods. The first idea is a method called BRDF, presented by Fantasias 3D, which was trying to solve a text-to-3D task. This is a method of predicting the color of a point using a simple MLP. We thought that this method could effectively solve global inconsistency, and we plan to apply only the part boxed in red in the picture. The second method, unlike baseline methods, auto-regressively rotates all camera views at each denoising step and then generates a partially undenoised image. We thought that global consistency would increase because images are created taking into account textures in all directions. Additionally, because only one texture map is used and updated during the entire process, it is memory efficient. For the experiment, we plan to use an observer's dataset. The dataset used by text-to-text for evaluation is publicly available, so we plan to measure performance using this dataset for a fair performance comparison. The FID score will be used as a metric to evaluate the experiment. It compares the similarity between an image set rendering the model's output and rendering the real textured 3D mesh from multiple camera views. This is our project plan. Thank you.
Hello everyone, this is a pitch presentation of Texturify++ of Team 12. Recent years we have seen remarkable progress in modeling 3D geometry. However, generating fully textured 3D objects remains a challenge that is less explored. This problem is discussed as a topic of texture generation. A 3D object is given as an input of a generator, and it creates an object with texture. Among various 3D objects, we'll focus on mesh representation. Our baseline paper is Texturify, a SOTA model that generates a random texture based on the given 3D mesh. The architecture of this model is divided into encoder, decoder, and discriminator. When an input shape is given to the model, the encoder extracts its surface features. Each output of encoder layers are connected to decoder layers to generate texture. Also, a StyleGAN-based latent code is mapped to a style code, which conditions the style of the texture. This model uses image and patch discriminators that takes 2D rendered view of the texture and real-world images. While other methods create blurry texture with a singular style, Texturify generates realistic and diverse texture on varying shape geometries like sedans, sports cars, SUV, and hatchbacks. Also, the dataset for this problem is usually consisted of mesh-labeled dataset with a paired texture images. In this paper, they assumed no one-to-one correspondence between meshes and texture images, making much more easier to construct a dataset.
However, there have been no experiments conducted on the multi-class object texturing using the Texturify model. The official code only supports single-class objects. As you can see in this figure, original Texturify model has no network that explicitly represents the class information of the 3D mesh inputs. In this enhanced model, we will incorporate a class feature network which classifies the type of object and integrate it with the original encoder component. It will encode given object to the latent space so that generator can utilize more information about the 3D inputs. This modification will guide our model in applying the appropriate texture to various objects. For our experiments, we will utilize the following dataset where each 2D images and 3D mesh objects are unpaired. To evaluate the performance of our model, we will employ FID and KID scores on the rendered 2D images. These metrics are widely used to assess the quality of the generative model. Lower value indicates the better performance. These are our detailed project plans and timeline. Thank you for your attention.
We're Team 13 and our project is on geometric deep learning for 3D shape correspondence. 3D shape correspondence is essentially a bijective map between vertices from one object to the other object, and depending on the type of transformation, this problem can become difficult because we need to model rigid or non-rigid transformations, or even transformations that don't respect the topology at all, which would mean that we would map multiple points from the first object to one point from the second object. And this would be useful in applications like recognizing different poses in motion of the same object, or self-similarity, or even shape morphing.
Freddy, if I define the problem definition. We define the task as predicting the shape matching between a mesh surface, ground truth reference mesh, and some query meshes. For the dataset, we use real scans, which are more accurate, like Faust. And for performance, we compute the point-to-point geodesic distances between the shapes without aligning the surface meshes.
Now, on previous work on deep learning on manifolds, we had local shape descriptors, which are essentially vectors that describe the edges or the vertices depending on the problem definition. And we can either work in spectral or in the spatial domain, where we can detect intrinsic correspondences between those features and between those shapes and those features. And in the spatial domain, if we work in the spatial domain, which is what we do in our project, it's more interpretable because we can see the convolution in non-Euclidean domain. As we can see it in computer vision, for example, it's more visual, more geometric. And for example, the heat kernel descriptor or the wave kernel descriptor, even shot, they are kernels that we can visualize, and we can visualize the geometry, as we can see from figure 8 or the geocon, because we define the convolution as the geodesic convolution. And the main idea and the things we try to improve in this project is to use MeshCNN to modify our network architecture without the global pooling layer, provide the fair comparison between learned and non-learned spectral and spatial descriptors for rigid, non-rigid, and non-topology preserving correspondences, modify the levels of discretization, and even use unsupervised shape descriptors for non-rigid transformation.
For the experimental setup, we will use the Faust Humans dataset, and the model will be implemented in PyTorch geometric framework, and we essentially want as a success criteria to improve the Princeton benchmark performance, which is the percentage of correct correspondences at different geodesic error thresholds. This finally is our plan and timeline for the rest of the weeks that are remaining. And thank you very much for your attention.
Let me present my project, Fine Marching Cubes Isosurface Distraction with Vertices of Arbitrary Accuracy. Problem definition. Its input is a continuous impulse function and iso level, and output is a triangular mesh, and there is no other supervision. That is unsupervised heuristic algorithm. As our previous work, the most famous thing is marching cubes, which we learned from the class. It first divides the space into cubes and detect iso level along edges, and then reconstruct a mesh. And the next breakthrough is geocontouring. On the vertices gotten from marching cubes, they calculate the vertex inside the cube based on the gradient of its input impulse function. They can represent a sharp edge. And next, these models adapted neural network from marching cubes and geocontouring. These are supervised models. And these are hybrid representation. It is a little bit different context, meaning that each grid cell has parameters for mesh, and they are trained with an impulse function together. And the aspect of isosurface distraction, they are similar to the previous models. So, motivation. Impulse function has full information of isosurface. Why do we have to rely on regularization techniques? Let's be fully dependent on the impulse function. In other words, let's search the impulse function as deep as possible. Then how to detect vertices of arbitrary accuracy feasibly? So here I came up with binary search. Binary search makes the search space half on each step, which means the accuracy increases exponentially. Practically, under 32-bit float operations, 24 steps provides the most accurate result. So, in the case where a line has two different signs on its end, the surface points can be found using a binary search with arbitrary accuracy. However, as you can see from the left figure, it cannot represent sharp edge. So, I came up with 2D binary search. From each surface having different signs on its vertices, find edge point using 2D binary search. However, as you can see from the left figure, it still cannot represent the vertices of a cube. So, I came up with a 3D binary search. To find the vertex point inside the grid cube, firstly calculate quadratic error function using points already found, and then do binary search to the direction. Then it can represent cubes perfectly now. Then, how to connect vertices found? Different from the original marching cubes, Fine Marching Cubes has vertices not only on lines but also on surfaces and inside the cube. So I analyzed the tessellation for 11 primary faces of Fine Marching Cubes, and I could extend these to tessellations for 22 basic cases. And these are the tessellations for all possible 256 configurations. So to summarize, it does not require gradients, and it can detect the sharp edges, and its computational complexity is almost the same with the previous heuristic algorithms, and GPU optimization is possible, and all vertices on the are on the isosurface with arbitrary accuracy, and it is intersection free and watertight. They are guaranteed, and there is no bias since it is not learning based. So regarding experiment, chamfer distance, F1 score, edge chamfer distance, edge F1 score, normal consistency will be used as metrics, and the data set collected by Miles et al. Will be used. Success criteria is to beat all metrics from previous models. This is plans and timeline. Thank you.
Hi everyone, we are Team 15 and I'm presenter Ki-nam Kim. My teammates are Junhyun Lee and Youngdo Lee. Let me introduce our project on overcoming camera-facing gaze bias in EG3D scene generation. In EG3D generated videos, when the face rotates, the gaze unnaturally looks toward the camera. We aim to fix this issue. In 3D, EG3D generated humans will always look forward regardless of their orientation. However, in the real world, the gaze direction should align with face orientation. The reason is EG3D used FFSQ dataset where most subjects look straight at the camera. Our approach uses the same EG3D input and output, but also includes gaze pose from a gaze estimation model. Recently, enhancing 2D GANs to 3D like Giraffe and EG3D has gained traction with high-quality 3D-aware synthesis. However, no prior work in this field has addressed the eye rotation issue. Building on that, let's delve into the framework of the baseline EG3D model. EG3D requires two inputs, a latent vector for facial attributes, and camera parameters. Transitioning from the baseline, our solution integrates a gaze estimation model with EG3D to determine gaze angles from face images. When you look at the image generated by EG3D on the left, you can see that the angle of the face and the angle of the eyes are not parallel. In contrast, in the real image on the right has them parallel. Therefore, our goal is to make EG3D align these two angles. We will fine-tune the pre-trained EG3D model using the following framework. First, we obtain the yaw and pitch from the camera parameters as ground truth. Next, we feed the images generated by EG3D into a gaze estimation model to obtain the gaze angles. And we calculate the MSE loss. Then we will use these gradients to train EG3D to generate the accurate gaze alignment. We will measure the image quality using FID and arc phase cosine similarities. Additionally, we will also use the IOU metric for the eyes in the generated videos to evaluate the eye rotation bias. Our success criteria includes achieving 95% of baseline performance and achieving 0.8 for the eye IOU value. Here's our timeline. We start with dataset preparation and select the gaze model. The following weeks focus on model implementation and refinement. By week 5, we finalize our work. Week 6 is for evaluation and reporting. This concludes our presentation. Thank you for listening.
Hi, we're Team 16, and we will present our project, Text-Guided Motion Editing with Inversion Technique. The emergence of diffusion models has led to significant advancements in text-to-image performance. Notably, Stable Diffusion and Imagen have made it possible to generate photorealistic images from user-provided textual descriptions. The principles of diffusion models have also found application in motion generation methods, making text-to-motion generation possible. However, while images have also achieved greater advancement in text-guided editing methods using diffusion inversion, text-guided motion editing still remains a challenging problem. While previous approaches have attempted motion editing using motion generation diffusion models, they often require manual joint masks to specify which body parts to be preserved and edited. Furthermore, these methods do not adequately account for the temporal and spatial alignment of different frames and body parts. To this end, we will present an approach for motion editing utilizing diffusion inversion techniques. Specifically, we will employ null text inversion to identify the optimal null text embedding. This approach will enable us to perform motion editing at our baseline. Our system overview can be summarized as follows. We create a diffusion inversion of motion diffusion models and then refine motions using techniques derived from image editing methods. Our experiments encompass both quantitative and qualitative evaluations. Quantitatively, we will assess our approach using metrics such as FID and arc precision to ensure the credibility of character movements. Additionally, we will conduct user studies to verify that our method produces natural results while adhering to user-specified text for motion editing. Furthermore, we will compare our results with the editing outcomes obtained from MDM and Flame, which are the most representative motion diffusion models. Our project plan comprises the following stages: data preprocessing, model development, evaluation, and report writing. Thank you for your attention.
Hi, I'm Kwang-Gyun. I will share our project titled Mesh Agnostic Audio-Driven 3D Facial Animation on behalf of my teammate Hyunho and Xiang. Audio-driven 3D facial animation is a task of generating facial animation that is synchronized to the input speech. In this task, the method has to perform deformation or generation of a 3D face model for the corresponding input audio. The most common approach for solving such tasks is to train a neural network with paired audio and facial animation data. While the method works well on the trained 3D face model, the trained network cannot be used to drive other face models because of different mesh structure or topology. Thus, for every new face model, a new network needs to be trained from scratch. Our goal of the project is to solve such difficulty using a mesh agnostic operation. Given an input audio and an arbitrary 3D face model, we want to train a neural network that can animate the face model given the speech. As mentioned, there have been numerous work that solve the task of audio-driven 3D face animation. However, those work are not mesh agnostic and works for the trained face model with same mesh structure. In contrast, deformation transfer field solve the problem with different mesh structures. Most recently, neural face rigging by Quinn et al. Has proposed a method to transfer the facial animation of a source model to an arbitrary target 3D face model. Thus, our concept is to combine both lines of work to achieve our goal. Here is an overview of our approach. First, we will closely follow the approach of Cole-Tucker and FaceFormer to extract audio feature using a pre-trained Wave2Vet2 model. Then the extracted audio feature is passed through a network that maps the audio feature for the latent code that correspond to meaningful mesh deformation. Lastly, we will use mesh agnostic operation used by Quinn et al. To generate the final facial animation using a mesh identity encoder and a decoder. After implementing our idea, we will use a standard benchmark data to evaluate the leaf vertex error to measure the synchronization. In addition, we would like to conduct a user study for better assessment. The tables shown in the slides are the expected outcome. Here are the plans for the project. Since there is no training data for such tasks, we are capturing and gathering data by ourselves. After gathering and filtering the data for 2 to 3 weeks, we will implement our main idea and improve upon the initial design for the next 4 weeks and continuously evaluate our method. Finally, we will wrap up the project for the last 2 weeks. Thank you for listening.
Hi, we're Team 18, and we're working on Sim Nerf to Nerf, editing 3D scenes with instructions through segmentation and in painting. We're on our performance improvement track. To begin with, let us introduce a novel 3D scene editing approach called Instruct Nerf to Nerf. It can edit Nerf scenes based on text instructions by utilizing 2D diffusion model. Please refer to the paper for further knowledge. Our main motivation comes from a geometric deficiency observed in Instruct Nerf to Nerf. While Instruct Nerf to Nerf is strong in geometric additions and changes, it struggles to delete or shrink geometric components as shown in the image on the right. Particularly the nose in the bear is not fully removed. To address this issue, we devised the idea of segmenting the object Nerf scene from the background Nerf scene. Applying the same 2D diffusion model gives a promising editing result when background scene is deleted. Our target of the project is to improve the 3D object editing based on the instructions. In the process, we'll utilize object segmentation and background in painting. The input consists of a user text prompt, such as put him in a suit, and the original nerf scene, while the output would be the edited nerf scene with smoother geometry. We have confirmed our idea by reconstructing one of the provided scenes in Instruct Nerf to Nerf dataset with almost no background, and this particular scene did not suffer from geometric distortions. Our next step is to utilize segmentation and inpainting. Before we move on to the main idea, we introduce two more previous works. SpinNerf is a remarkable method for segmenting the object scene and inpainting the background scene. The GIF in the middle is a demo of SpinNerf, and we can see that it seamlessly performs background inpainting. And FallSDF presents better geometry representation than Nerf. We will apply this method to enhance the geometrical coherence in the object edition and compare the results. This is our main idea. Starting from the original dataset image, we employ SpinNerf to segment the object scene and inpaint the background scene. For the object scene, we selectively apply Instruct Nerf to Nerf with the given text prompt to produce 3D edited object scene. And finally, we place the edited object on top of the inpainted background scene in 3D space. Since the two 3D scenes share the same camera coordinates, the integration wouldn't be a problem. Our project performance improvement will be assessed through two measures. For qualitative results, we will compare the generated scenes based on the same dataset with Instruct Nerf to Nerf. Quantitative improvements will also be evaluated using CLIP, which estimates the temporal consistency and alignment between result and the given text prompt. Our team's plans and timelines are as follows. Important events or dates are emphasized in bold. We look forward to sharing the final project poster and report with all our classmates and the professor. Thank you for listening, and we hope you enjoyed it.
Hello, we are Team 19, and we are gonna introduce about our project, diffusion-based video synthesis from 3D sparse frames. In today's digital age, video content has become increasingly popular for information sharing. However, one major challenge is the growing size of video files as frame rates increase. To tackle this challenge, we propose a solution that inferring intermediate frames between the initial and final frames of a video sequence. This approach can significantly reduce storage requirements while maintaining video quality. The key idea here is to generate a 3D video based on this concept. Our project's primary goal is to create 3D videos using the initial and final frames of a moving object. We take input as initial and final frames from various angles, and the output is a video such that smoothly transitioning between these frames. We make the assumption that the video images are 800 by 600 pixels with a duration of 1 second at 60 Hz. Our main idea is to generate frames using a diffusion model. Then we repeat the frame generation process for multiple views to create a full-fledged 3D video. To achieve this, we've adopted a baseline method for frame generation based on a research paper. As you can see from the images we're generating using this method, the diffusion model can smoothly transition behaviors within the video. In addition, we've referred to another paper as a baseline method for producing 3D videos based on images from various angles. The video you are currently watching is a result of our work, influenced by this paper. Our ultimate goal is to produce results like this. To achieve this, we have carefully selected 3 types of videos that are easy to synchronize between views and provide a rich dataset for multi-view images input. We are evaluating our success based on metrics with MSE loss and the visual naturalness of generation videos. Here's our project timeline, detailing the steps and milestones we'll be following to achieve our objectives. And now, this is it. Thank you for your paying attention.
Hello everyone, I'm Kang-Sang Kim, and I'm going to introduce my project named Improve Point LLM using in-context learning and 2D images for 3D point cloud understanding. Following the rapid growth of LLMs, studies have begun to apply them to the 3D vision domain. This is mainly because we can actively communicate with the model and leverage the best amount of knowledge it has. These benefits become more important, especially when the output type is text-based, like 3D captioning. And this is the problem definition. LLM-based model gets a 3D point cloud and a question as inputs, and produce an open vocabulary, class name, or description according to the question. As you can see, the model should say what it is and a description of the color, shape, and components of the point cloud. My baseline paper, Point LLM, made point tokens align in the text space using point encoder and projector. It was tested for 3D classification and captioning tests, but it can also talk anything about a given point cloud. There are two main ideas to improve Point LLM. The first one is to use in-context learning, which is emergent behavior in LLMs, where the language model performs a task by conditioning on input-output examples. So not just putting one test sample during evaluation. I guess if I give a few demonstrations from the trained dataset that are related to the test input, then the model might consider the examples and predict the class label more accurately. The second idea is to use 2D rendering images of point cloud in different views to give more information to the model. So I will give image information to the model with image tokens produced by image encoder. And I suppose if the model has more information about the point cloud, then the model can make more precise caption for it. I will use Cap3D dataset for two tasks. I will evaluate the model with ChatGPT for the classification task. And I hope this in-context learning can improve the accuracy by 2%. For 3D captioning, I will use ChatGPT and SimSCE metrics for quantitative evaluation and human evaluation for qualitative one. I hope my methods improve the performance by 3%, 3%, and 5% for each metric. This is my plan for this project. I will finish the first idea experiment by November 6th and finish the second one by November 26th. This is the end of my presentation, and thank you for listening.
We're Group 21 and we decided to work on novel problem solving. The main goal of our project is enhancing performance of NeRFDAT within light variance. The reference paper highlights that NeRFDAT struggles in outdoor settings due to challenges posed by rapidly changing light sources. As a multi-view model, NeRFDAT requires consistent lighting within each scene to achieve precise 3D detection. However, it's worth noting that even indoor environments, unless they are perfectly sealed, can be susceptible to variation in lighting. With this in mind, our mission is to address the shortcoming by creating a version of NeRFDAT that is invariant to light source changes. Here's the architecture of NeRFDAT model. It is divided into 3D detection branch and NeRF branch. In the 3D detection branch, the result from the 2D image backbone is inputted into the feature pyramid networks to produce the 3D feature grid. From this feature grid, positions are encoded and then applied to the MLP learned in the NeRF branch, resulting in the extraction of density to produce the opacity grid. Combining this with the original feature grid, detection is carried out. Light variance can be thought as a specific kind of perturbation studied in adversarial attack. We believe such special case of light variance perturbation can be trained with a model. Here's the brief architecture and logic behind the light variance perturbation model we aim to build. Let's say the original scene had a light source at point A. Let's render the scene into a 2D image from a specific angle. If we feed this image as input along with the target light source position represented as B on the slide, which is different from point A, our model will return a rendered 2D image of the same scene from same angle, but as if light source was located at point B. Leveraging the model introduced in the previous slide, we plan to generate the augmented dataset based on the ScanNet dataset, the original dataset used in the reference paper. Our strategy involves producing additional 2D images that represent varied lighting conditions within each scene. By doing so, we aim to enrich the dataset with image rendered from multiple light sources, showcasing the capabilities of our model in addressing light variance challenges. Developing upon idea, we will add a part which extracts light identity feature on the original NeRFDAT architecture, which is labeled as inverse function of f. What we mean by light identity feature extraction is the conversion of original light source position of each scene into a reference point that we define. Then, despite the varying light source position of input among each scene, our model is capable of regarding them as same input and simply adding the light source feature during the rendering process, which is labeled SG. The 10 indoor scene that we actually obtain in real life will be used as evaluation set. As evaluation metric, mean average position will be used. If we successfully build our model should outperform the original NerfDet within the 10 indoor scene that we obtained and perform similar within the original ScanNet dataset. And here's the plans for the rest of the weeks. Thank you.
Hello, my name is Sung Ha, and I'm on the performance improvement track. I'll be working on augmenting hierarchical representation network with occultation segmentation. "3D face reconstruction is a gateway to immersive experiences in AR/VR, personalized medical treatments, and realistic characters in film production. Despite advancements, creating detailed face models from limited view images remains a formidable task. The true essence of facial features, especially in minute details, often get lost in translation. For our problem, the inputs are portrait images of size n by n, and the output is 3D scans of the facial features. For training, 2D scans are used for getting 3D priors of facial details and are used as ground truth data. One of the key reconstruction method is 3D morphable models, which is a generative model for face shape and appearance that is based on two key ideas. First, all faces are in dense point-to-point correspondence, which is usually established on a set of example faces in a registration procedure and then maintained throughout any further processing step. Other method predicted displacement maps via pix-to-pix HD network and combine them according to blend shape weights for dynamic detail synthesis. Despite successes, capturing mid-frequency details remained elusive. Efforts to balance both mid and high-frequency details often led to compromises, leaving room for improvement. In the baseline, we first employ 3D-MM to predict coarse, mesh, and albedo. Then we use a hierarchical modeling strategy to handle the complex facial details in a coarse-to-fine manner. In addition to the baseline method, we augmented training with a segmentation model of occultation to create an additional deformation map. We plan on using chamfer distance, NMSC, and mean normal error as the major evaluation methods. We want to achieve statistically significant improvements in those areas, and especially for partially occluded faces. These are our plans and deadlines. From week 3 to 4, we want to focus on augmenting the original model with segmentation models. From week 5 to 6, we want to submit the first interim report. From week 7 to 8, we want to conclude the submission of project interim report and finalize the project report in code. Thank you for listening.
In CS479, I would like to reduce the execution time of the texture method. Let's first point out what the texture method is. The texture method is a diffusion-based method that generates a texture map that can be applied to the given 3D mesh. In each iteration, method selects a different viewpoint and generates. First, it creates depth map, image, camera normal, and viewpoint cache from the viewpoint. Trimap identifies where to be created, and the diffusion process creates the image. Finally, it modifies the texture map by projection. After enough iterations, a complete texture map will be generated. The most important part of the texture methods are quality and runtime. But to improve this, there is something to be considered. First, how to reduce runtime. In this project, I will introduce a way to generate in parallel. For quantitative evaluation, I will use FID and KID to measure. Here is the main idea. First, create a number of random candidate viewpoints. From the viewpoint cache evaluation, I can choose a viewpoint without overlapping rendering part. In the baseline method, creation could not be parallelized for each iteration because there was a region conflict between viewpoints. With this viewpoint, texture map generation can be parallelized. I aim to halve the number of iterations and reduce the execution time during the projection phase. Datasets will be object format 3D file provided by ModernF4T. Metric will be execution time, FID, and KID. I aim to deduce 20% of execution time within 10% FID and KID changes. These are the major objectives, and I aim to achieve each major goal every 2 weeks. Thank you.
Hi, this is Team 24. My name is Sangmin Lee, and our team members are Hyojin Jang and Hyunbin Lee. Today, we are going to present about ShapeBind, a novel embedding model binding 2D image, 3D structure, and text. ShapeTalk is the state-of-the-art paper for the text-driven 3D deformation, but we figured out that ShapeTalk is weak at extrapolation. If there is no 3D structure dataset about a certain shape, then we're not able to edit based on that shape information. Instead, we perform extrapolation by binding the latent space of the other domains such as 2D image. We have the similar problem definition as ShapeTalk. We input 3D point cloud data and deform it using text prompt.
ShapeTalk introduces a 3D point dataset with others, named ShapeTalk, and a 3D shape editing framework, Change3D, which takes the target 3D shape and edits the shape by the text script given as a goal. The training of Change3D is in 2 stages. In the first step, Shape Autoencoder and Neural Listener is trained. The Neural Listener takes 2 shape latents and target script and outputs probability of likeliness between 2 shapes. In the second stage, shape editing is trained by structuring a pipeline with the trained autoencoders and Neural Listener. ImageBind is an embedding model that takes cross-modal data and maps to the same latent space. This makes it possible to calculate the distance between 2 cross-modal data. ImageBind combines 4 models: audio, image and video, depth and text. Here is an example of ImageBind.
So we present a novel embedding model. ShapeBind not only combines text and image in the same embedding space, but also includes 3D. This works by contrastive learning using the latent space from each encoder. And second, we may change H3M model. The editor takes deformation from text and the target shape latent vector to do proper modification to the latent vector. Since all the latent vectors are in ShapeBind embedding space, deriving the cosine similarity between the modified latent vector and the encoded text latent vector shows distance between the two and can be used as a loss to train the editor. There is another method. We use the idea that latent variables are good over-representation for the various features. Since we force the 3D, 2D, and text embeddings into same latent space, we can different specific feature using compound of arithmetic expressions like addition and subtraction.
We utilize 4 different datasets for ShapeBind training. Clip, OpenClip, and Lion 5B dataset are image-text pairs. ShapeTalk dataset are 3D shape text pairs. ClipForge dataset are 3D shape rendered image pairs. This dataset enables training multimodal embeddings.
Quantitative metrics are same as ShapeTalk. Many of these metrics use chamfer distance. Since we cannot easily evaluate tasks such as extrapolation and deformation by quantitative metrics, we have to check the performance by human eye or methods like identity penalty. This is our plan. You can check the details later. Thank you for listening.
Good morning, good afternoon. Let me explain what point cloud registration is. Let's think of a robot, autonomous robot like this, which is equipped by a laser scanner. And as the robot moves inside the environment, it generates point cloud data, and at some point later, it generates other set of point clouds. So our problem is to align these 2 sets of point clouds so that we can make our robot autonomous. Let me explain this in a very simple fashion. So these are some sort of point clouds that are generated at some point, and these are another set of point clouds that are generated at some later point. And our problem is to find the correct rotation and translation so that these 2 sets of point clouds align with each other. So in line with your previous understanding of point cloud registration, this work specifically focuses on aligning two partially overlapping point clouds donated by X and Y here and finding the transformation, in other words, rotation and translation between these 2 point clouds so that we're better be able to align these point clouds. This is more like an application of 3D reconstruction, as you can see. So my work will be based on a paper called GeoTransformer, which is the state of the art, and it works. Basically, the architecture works in 3 different modules: which extraction, which basically downsamples point clouds, and superpoint matching, and point cloud matching for like extracting more accurate superpoint correspondences, and then the final step basically gives us the rotation and translation. So the main idea of this of my work will be basically eliminating the limitations of GeoTransformer by designing a new self-attention mechanism. So that will be that will definitely that will be done by modeling the relationship between points in the point cloud and using this information to guide the registration process. And other improvements that I'm considering to make are the following. And as for experiment setup and success criteria, I'll mostly be experimenting with working on 3D LO match data benchmark. LO means limited overlap. And I'll be trying to outperform GeoTransformer in terms of these following 3 metrics. So this is my tentative plans and timeline.